This episode of Real Engineering is brought to you by Brilliant.org, a problem-solving website that helps you think like an engineer. There is over 4 billion mobile phone users in the world, a figure that is expected to grow to 5 billion by the end of the decade. We've all become hugely dependent on this amazing tool, and the feeling of it running out of battery is all too familiar, that desperate scramble before it goes gently into the night. These devices last, at best, about one full day on a charge, and then must spend the better part of the evening tethered to a wall. Unless you are constantly carrying your charger with you, it is difficult to keep your phone from dying over the course of a busy day. But what if we could charge our phones conveniently, without having to find a plug and carrying a charger with us at all times? With the proliferation of electric cars and electronic biomedical devices like pacemakers, one vital piece of technology, first developed about a century ago, is set to significantly improve the way we keep our devices powered. It's called wireless charging, and it's popping up in cafes, fast food restaurants and IKEA furniture. Although there are competing standards, wireless charging is power delivery from a power source to an electronic device without the need for a tethered wire connection. Inductive charging is the most popular form of wireless charging for mobile devices, and leading the way is the Wireless Power Consortium with their Qi Open Interface standard. Using fundamentally the same technology, other groups are incorporating inductive charging tech for use in electric vehicles. Getting to the bottom of inductive charging, you need to go all the way back to the mid-1800s when Michael Faraday discovered the underlying principles of electromagnetic induction. He discovered that in the presence of an alternating magnetic field, an electromotive force would be produced across an electric conductor. By the late 1800s, Nikola Tesla utilised this idea and demonstrated the phenomenon of resonant inductive coupling by lighting an incandescent lamp wirelessly. By tuning the current to match the resonant frequency of the coils, the two coils would couple, providing higher efficiency power transfer. The discoveries that stemmed from Faraday's led to the modern electrical motor and other unmeasurably important inventions. However, for inductive charging, the science proved easier than implementation. For starters, there weren't many electronics that would greatly benefit from such technology in the days of Nikola Tesla, and due to limitations in circuit board design and size constraints, it wasn't until the 1990s and 2000s that the technology became viable at the consumer electronic level, where we started seeing wireless charging toothbrushes and in 2008, wireless charging mobile phones. An inductive charger consists of only a few parts: AC current from the wall, an oscillator electrical circuit, and the transmission coil. The transmission coil is a tightly wound copper element that, as the alternating current passes through, will produce a magnetic flux. The magnetic flux density is based on things like the number of turns in the wire, the diameter of the transmission coil, the distance from the coil, and other properties such as current. On the receiver's end, the process is basically the same except opposite. In the receiver device, a coil of the same type is embedded into the charging circuit. The alternating magnetic field is picked up by the receiving coil and a current is induced. The AC power is passed through a power rectifier and stabilizer to convert it into DC power the phone can use to charge the battery. Both the transmitter and the receiver have electrical resonant frequencies designed to be the same. For low displacement distances, such as a mobile phone on a charging pad, it is actually less efficient to operate at the circuit resonant frequency due to heat generation. However, for a larger displacement distance, such as a car parked over a charging pad, operating at the resonant frequency causes inductive coupling to counteract some of the displacement-related transmission losses. There are many other factors that affect performance of transmission, and with no standardized design on the phone's end yet, charging pads need ways of detecting the type of device it is charging, have multiple coil arrangements, and control modules to alternate between modes. The two big questions with inductive charging are ones we keep coming back to. Do people really care about the technology, and what are the implications of inductive charging becoming popular? Having a fully charged phone wirelessly but nonetheless stuck to a charging pad is barely a convenience. Teams are working within the Qi wireless standard to create devices such as the Pi charger, which can charge up to 4 devices at a range of up to a third of a meter with a max power output of 10 watts per device. It's completely conceivable that the office furniture of the future will have inductive charging capability built in, followed by most laptops, cell phones and wireless mice. But consumers need to care about it, and hardware manufacturers need to see the value. There is one industry that inductive charging will make a meaningful impact, and it happens to indirectly involve Tesla once again. Going to the petrol station is a legitimate inconvenience, and visiting a Tesla charging station is an even bigger inconvenience. That's why startups and corporations alike are beginning to shift their attention to this lucrative opportunity. Similar to charging a cell phone on a charging pad, a transmitter would be installed in parking spaces and a receiver on the bottom of the car. Imagine your autonomous electric vehicle dropping you off for dinner and seeking out a parking space with inductive charging. No attendant needed, the car simply aligns itself with the transmission pad and the charging process is initiated. If these industries can make this tech convenient, there is a huge chance people will want to use it, but is that a good thing? According to a study in 2015 conducted by the Wireless Consortium, the creators of the Qi standard, they found in real-world conditions the Qi wireless charger had an efficiency of about 59.4%, with their competitor coming in at just 39.6%. With 30 million iPhone X sold in its first quarter, they have an impact of 415 megawatt hours per day if charged fully once per day. With an efficiency of only 60%, that would result in an increase in 278 megawatt hour load on the grid, which is about 25 years worth of power for an average home. This is only accounting for one mobile phone and not accounting for the other 2.5 billion smartphones projected to be in use by 2019. If all had inductive charging, the impact could be over 23,000 megawatt hours consumed per day. To produce this power cleanly, the added load would require an additional 1,400 wind turbines just for the added load. With electric vehicles, things can get even more interesting. The Tesla Model 3 is getting between 4.5 and 5.5 kilometers per kilowatt hour, depending on driving habits. With a daily commute of 35 kilometers, a Tesla uses 7 kilowatt hours, or almost the same power usage as a small family home. So for every EV on the road, it's similar to adding another house on the grid, and when you introduce inductive charging, it can equate to adding nearly 2 additional homes. National power grids can likely accommodate this growth, but local infrastructure may not be capable or even willing to expand their capacity for the sake of convenience to EV drivers. A lot of the added stress on the grid is based on the fact inductive charging is an inefficient technology, but that may not necessarily be true forever. Oak Ridge National Lab recently demonstrated a 20 kilowatt inductive charging system that operates at 90% efficiency, with power delivery up to 3 times faster than traditional wired charging. Although it's too early to know what the real-world wall-to-battery efficiency will look like, it's still promising to see some of the sharpest engineers in the energy field digging deeper into the technology and beyond. Theoretically, it is possible to transfer energy over greater distances with electromagnetic waves. NASA awarded one company $900,000 for its laser-powered climbing robot. The robot had no power source on board and managed to climb 900 meters up a cable suspended from a helicopter in just under 4 minutes, using a high-powered laser to provide enough energy to solar cells on its undercarriage. This is a fascinating technology that could have huge potential. We could have huge solar cells in space beaming down energy to Earth or other satellites, but right now the power lost in transmission is far too great to be useful, and this is a problem that is really facing current technology on Earth, whether we want to acknowledge it or not. Learning about simple core concepts like this that shape our world allows us to apply our knowledge to real-world problems. If you're watching my videos, you're likely like me. You are enthusiastic about science and technology and want to apply that knowledge to your everyday life. But to do that, you have to truly understand these principles yourself. Maybe you are an IT professional and want to brush up on your understanding of how computer memory works. Well, I have the perfect place for you to do that. You could take the brilliant course in computer memory. This course is one of many you can take on the site, but today I'm going to focus on what you will get from this specific course, because I took it myself and I knew very little about memory before I started. The course treated me like I treat my viewers. I expect them to have at least a high school level understanding of physics. There were terms in there that took me time to understand as I puzzled through the questions, which helped me actually learn and get true knowledge of the subject. The course checked my understanding along the way, and if I wasn't completely confident on my understanding, I could check the solution, which reinforced my learning and corrected my misconceptions. I came out the other end with a better understanding of how computers work and why that information would be important to a software developer. My videos are primarily crafted to inspire, but Brilliant is crafted to educate, and that's why they are the perfect way to wrap up my videos. To support Real Engineering and learn more about Brilliant, go to brilliant.org/real engineering and sign up for free. And also, the first 73 people that go to that link will get 20% off the annual premium subscription. The channel's views have been going down lately and I'm not sure why, but there has definitely been a shift in the algorithm and a lot of the educational channels that upload infrequently are feeling the pressure. So please hit that bell button and get notified when I upload, and do it for your other favourite creators too.